Welcome back, everyone, to our ongoing deep dive into the OEIS, that amazing online encyclopedia of integer sequences. If you're new here, just picture a giant digital library. But instead of books, it's packed with number patterns. That's the OEIS in a nutshell. And we've been exploring it through the lens of number theory. Today we're going three-dimensional with sequence I000162. This one delves into counting something called polycubes. And you know what? If you've ever played with building blocks or tried to cram oddly shaped luggage into your car, well, you've already dabbled in the world of polycubes, maybe without even realizing it. To help us unpack all this, we have a Fields Medal-winning mathematician with us today. They're known for making even the most mind-bending math feel surprisingly down to earth.
It's great to be here.
All right, so this sequence, I000162, it starts off pretty simple, 112829. But then things escalate quickly. What's the story these numbers are telling us about building with cubes?
Well, those numbers represent how many unique polycubes you can make using that specific number of cubes. So the first one, that's just a single cube by itself. Then the next one, that's two cubes stuck together. Not a lot of variety there, right?
Right.
But when you hit 2, meaning we're using 3 cubes, now you start to get some choices. You could have a straight line of 3 or an L shape.
Okay, I see that. But then that jump to 8 when we get to 4 cubes. I mean, I get that more cubes means more options. But are there really 8 distinct ways to arrange just 4 cubes?
Oh, there are definitely 8. And this is where visualizing things starts to get a bit tricky. You might initially think of just the simple arrangements, right? Like a straight line of 4 or a square shape. But when you start rotating those and considering mirror images, the possibilities really multiply.
Ah, like a left hand and a right hand. They're both hands, but one's a reflection of the other.
Exactly.
That's what's called chirality, isn't it?
Yeah.
And that matters when we're counting these polycubes.
Absolutely. Chirality plays a big role. A chiral polycube is just like your hands. They're mirror images, but you can't just rotate one to perfectly match the other.
Okay, so it's not just about the shape itself.
Yeah.
But also its orientation in space.
Exactly. And in this particular OEIS sequence, reflections are counted as different polycubes. That's how we get to 8 for those 4 cube arrangements, which are technically called tetracubes.
Tetracubes. I like that. I was reading that there's actually 2 ways to count these things. One where reflections are unique, like we're doing here, and another called the free count, where they're treated as the same.
That's right. There are different conventions depending on the specific context. So our sequence, A000162, this one gives us what's called the one-sided count, which results in those 8 tetracubes. But if we were using the free count, we'd only have 7 tetracubes, because 2 of them are just mirror images of each other.
And get this, Wikipedia mentions that the classic Soma cube puzzle uses both forms of those mirror image tetracubes. I always love finding those real-world tie-ins.
It's fascinating how these concepts show up in unexpected places.
It really is. But let's get back to those numbers in the sequence. We go from 166 hexacubes, that's for 6 cubes, to a whopping 123 heptacubes for 7. It's like the number of possibilities just explodes as we add more cubes. Is there a name for this rapid increase?
It's called combinatorial explosion.
Combinatorial explosion.
And it's a fundamental concept in mathematics and computer science. As you add more components to any system, the number of possible arrangements skyrockets. It's like if you're cooking, think about having a handful of ingredients versus a whole pantry full. Your recipe options go through the roof with that pantry.
So polycubes aren't just child's play then. They're actually demonstrating this fundamental mathematical principle.
Exactly. They're a tangible way to visualize combinatorial explosion.
The Wikipedia mentions they're connected to even more math concepts. Things like tilings and lattices.
Oh, absolutely. Polycubes have deep connections to those areas.
What's the link there?
Well, tilings explore how shapes fit together perfectly to cover a surface. No gaps or overlaps. Imagine tiling your bathroom floor. But now think about doing that in 3 dimensions. Polycubes can be the building blocks for certain 3D tilings.
Okay, I'm starting to see how this goes beyond just blocks. Then there's lattices, those regular grids of points in space. How do those relate?
Think of a lattice as a framework, and certain types of lattices can be analyzed using, you guessed it, polycubes. Their structure can be represented and understood using polycube arrangements.
All right, and this is where my brain starts to melt a bit. Wikipedia also mentioned something about a tesseract, a 4-dimensional hypercube unfolding into a specific octacube. It's called the Dali cross. This sounds like something straight out of science fiction.
It does sound a bit like that, but it's a fascinating concept.
Are we really about to talk about 4 dimensions through the lens of building blocks?
It's more connected than you might think. It's like if you unfolded a cardboard box to lay flat, you're taking a 3D object and representing it in 2D. Unfolding a 4D hypercube into our 3D world can similarly result in a polycube shape, and the Dali cross is one example of that.
Hold on, I need a second to picture that. So we're essentially unfolding a shape that exists in a dimension we can't even see, and it ends up looking like something we can build with blocks.
Exactly, that's the fascinating part. And what's even more intriguing is that Salvador Dali, the surrealist artist, he actually featured this octacube, the Dali cross, in his 1954 painting Crucifixion, Corpus Hypercubus.
No way. He was clearly intrigued by these higher dimensional ideas.
It seems so.
That connection to Dali is blowing my mind. We've gone from building blocks to four-dimensional art in the span of a few minutes.
It's quite a journey, isn't it?
It really is, and Wikipedia mentions a couple more intriguing properties of polycubes: boundary connectivity and dual graphs.
Ah, yes, those are key concepts.
Yeah, I was wondering about those. Boundary connectivity sounds like it deals with, well, the boundaries of these shapes.
It gets into how the surfaces of polycubes connect. Some can have holes or disconnected boundaries, which adds another layer of complexity. And a dual graph, that's a way to visualize a polycube's structure. You use a network of points and lines. Each point represents a cube, and the lines show which cubes are connected.
So we have all this geometry going on, but we're talking about this on a podcast about the OEIS, which is all about number theory. How do we bridge that gap?
That's where the true power of the OEIS comes in. It allows us to connect seemingly disparate areas of mathematics. We can use number sequences and other tools of number theory to study these geometric properties. For example, we can look at sequences related to the number of polycubes with a specific surface area, or the number of ways to arrange them in a tiling pattern. These sequences then give us numerical insights into the geometric characteristics of polycubes.
So it's like we're finding numerical codes embedded within these 3D shapes. By cracking those codes, we can unlock a deeper understanding of their geometry.
Precisely. And that's just the beginning. And what's particularly fascinating is how we can move beyond simply visualizing these polycubes, and actually translate their geometric properties into the language of numbers.
So instead of just seeing shapes, we can actually describe them using numbers.
Exactly, and by doing so, we can analyze them using the powerful tools of number theory. Think of it like this: we're uncovering hidden numerical codes within these 3D shapes.
That's a really cool way to think about it. But for those of us who might be new to number theory, what are some of the key concepts we need to understand to crack those codes?
Well, one fundamental concept is that of counting. We've already touched upon this with the OEIS sequence, A000162, right? Which tells us how many polycubes exist for each number of cubes. To truly understand this sequence, we need to delve into combinatorics, which is all about counting and arranging objects.
So combinatorics helps us understand how many different ways we can put those cubes together.
Precisely. And remember our earlier discussion about chirality. Symmetry also plays a crucial role here. When we analyze the symmetries of a polycube, we're essentially looking for patterns and transformations that leave the shape unchanged. And those symmetries can be described using mathematical groups, which are algebraic structures that have deep connections to number theory.
Okay, my brain is starting to make some connections here. We've got geometry, combinatorics, and now algebra all intertwined in the world of polycubes. It's amazing how these different areas of math start to blend together.
And that's just the beginning. Polycubes also have connections to graph theory, where we can represent their structure using networks of nodes and edges. Each node in the graph represents a cube in the polycube, and the edges represent the connections between them.
So we can actually draw a diagram that shows how the cubes in a polycube are linked together.
Exactly. These diagrams are called dual graphs, and they can be incredibly useful for analyzing the properties of polycubes. And the really cool part is that we can then use tools from both number theory and computer science to study those graphs and gain even deeper insights into the polycubes they represent.
It sounds like polycubes are a gateway to a whole network of interconnected mathematical concepts.
They are, and it's not just a one-way street. Polycubes don't just help us understand other areas of math. They can also be used to illustrate and make sense of number theory concepts.
So instead of just using numbers to understand polycubes, we can also use polycubes to understand numbers.
Precisely, for example, they can be used to visualize the concept of partitions of integers. Think of taking of a polycube and splitting it into smaller polycubes. That's analogous to taking an integer and breaking it down into smaller integers that add up to the original number.
Oh, that makes sense. It's like using building blocks to represent numbers. We can see how different combinations of smaller blocks can be used to build a larger block, just like different combinations of smaller numbers can be used to make up a larger number.
Exactly. By using polycubes as visual models, we can gain a more intuitive understanding of these abstract number theoretic ideas. It's like having a concrete representation that helps us grasp the underlying concepts more easily.
So for our listeners who are number theory students, what's the key takeaway from all of this? How can exploring polycubes enrich their understanding of number theory?
I'd say the biggest takeaway is that even seemingly simple objects like polycubes can be incredibly rich in mathematical meaning. By exploring them, we uncover connections and insights that bridge different areas of mathematics, combinatorics, algebra graph theory, and of course, number theory.
It's like polycubes are a meeting point for all these different mathematical ideas.
Exactly, and the beauty of the OEIS is that it provides us with a platform for exploring these connections. By studying sequences like A000162, we're not just learning about polycubes, we're also gaining a deeper understanding of the underlying mathematical principles that govern their behavior and connect them to other areas of mathematics.
So we've established that polycubes aren't just about building blocks. They're a gateway to a whole world of mathematical exploration. But what if we take it a step further? What are some of the more advanced or specialized areas within number theory where polycubes might come into play?
That's a great question, and it gets to the heart of why research in this field is so exciting. One avenue is exploring the specific number theoretic properties of the A000162 sequence itself. Is there a formula, some elegant equation that predicts how many polycubes exist for any number of cubes? Or are there hidden relationships between this sequence and other sequences in the OEIS, hinting at deeper connections we haven't uncovered yet?
It's like we're searching for hidden patterns and relationships within this vast sea of numbers.
Precisely. And then there's the computational side of things. How do we actually generate and list out all these polycubes, especially as the number of cubes gets large? Can we design clever algorithms that exploit the symmetries and properties of polycubes to make those computations more efficient? These questions bridge mathematics and computer science.
So even coding and programming can become tools for understanding these shapes.
Absolutely. And as our computational tools become more powerful, we can tackle even more complex polycube problems, leading to who knows what new mathematical discoveries.
This deep dive has really opened my eyes to how much more there is to polycubes than meets the eye. I'm starting to see them everywhere now, in furniture, in architecture, even in the way molecules are structured.
That's the beauty of mathematics. It's all around us, often in places we least expect. And by cultivating a curious and observant mind, we start seeing those mathematical patterns and structures underlying our world. It's like unlocking a secret code that reveals the hidden order and beauty of things.
I love that analogy. But before I get too philosophical, I'm also curious about the practical applications of polycubes. We've talked theory, but where do they actually make a real-world impact? They're not just theoretical constructs after all.
That's a great point, and it's something we'll explore in detail when we return for the final part of our deep dive.
Welcome back to the deep dive, everyone. We've been on quite a journey with these polycubes, these fascinating 3D shapes built from cubes. We started with OEIS A000162, that sequence that counts them. Then we dove into their mind-bending connections to higher dimensions and all sorts of other math concepts. But we left off with a really intriguing question. How does all this theory translate into real-world applications? Where do polycubes actually make a difference outside the realm of, pure mathematics?
It's a great question, and it highlights how even the most abstract mathematical ideas can have surprisingly practical implications. One area where polycubes really shine is in packing problems.
Packing problems. So like when I'm trying to fit all my groceries into one bag.
Yeah.
Or those Tetris-like puzzles where you have to arrange the blocks perfectly.
Exactly. But imagine those puzzles on a much larger scale. Think about a shipping company trying to fit as many boxes as possible into a shipping container, or an architect designing a building and figuring out how to best utilize the space. These are real-world scenarios where understanding the properties of polycubes can make a huge difference.
So it's like 3D Tetris, but with real-world consequences. A misplaced polycube could mean wasted space, wasted money, or even a structural instability in a building.
Absolutely. And things get even more complex when you factor in irregular shapes, which are common in real-world packing scenarios. But even then, the principles we learn from studying polycubes, their volume, their surface area, how they fit together, those provide a foundation for developing efficient packing algorithms and strategies.
It sounds like polycubes are the unsung heroes of logistics and spatial optimization.
Yeah.
But are there other applications beyond just packing things efficiently?
Oh, definitely. Another area where polycubes are making waves is in the world of chemistry and materials science. Remember how we talked about molecules being atoms bonded together in specific 3D configurations? Well, some of those molecular structures can actually be modeled using polycubes.
So those molecular model kits we used in chemistry class, with the little balls and sticks representing atoms and bonds, are those basically polycubes in disguise?
You could say that by representing molecules as polycubes, we can visualize their shapes and study their properties in a more tangible way. This can help us understand how molecules interact with each other, how they bind to surfaces, and even how they behave in chemical reactions.
So from something as massive as a shipping container to something as tiny as a molecule, polycubes are providing insights and solutions. It's amazing to think that these abstract shapes are playing a role in understanding the building blocks of matter itself.
And the applications don't stop there. The world of computer graphics and game design is also benefiting from the power of polycubes. Think about video games that involve building structures or manipulating objects in a 3D environment. Polycubes can be used as the basic building blocks for these virtual worlds, allowing designers to create complex and realistic environments from simple geometric shapes.
So those world-building games where you can stack and arrange blocks to create anything you can imagine, are those leveraging the power of polycubes?
They are. And what makes polycubes so appealing in this context is their balance between simplicity and flexibility. They're simple enough to be computationally manageable, yet flexible enough to create an incredibly diverse range of shapes and structures.
It's like they're the perfect blend of mathematical elegance and practical utility. We've gone from packing boxes to building virtual worlds, all thanks to these unassuming polycubes. As we wrap up this deep dive, what's the key takeaway you hope our listeners, especially those studying number theory, will remember?
I think the most important message is that mathematics, even in its most abstract forms, has the potential to impact our world in profound ways. Polycubes are a perfect example of how a seemingly simple mathematical concept can bridge the gap between theory and application. From optimizing shipping routes to designing life-saving drugs to creating immersive video games.
It's a reminder that curiosity and a willingness to explore those seemingly abstract ideas can lead to unexpected and incredibly impactful discoveries.
Exactly. The OEIS, with its vast collection of integer sequences, is a testament to the power of observation and pattern recognition. By exploring sequences like A000162, we're not just expanding our mathematical knowledge, but also opening our minds to the interconnectedness of different fields and the potential for applying those insights to real-world challenges.
So the next time you see a child playing with building blocks, remember that they might be unwittingly engaging with a mathematical concept that has the power to shape the future. And to all our listeners, I encourage you to continue exploring the OEIS. Every sequence holds a hidden world waiting to be discovered, full of patterns, connections, and surprises.
And who knows, maybe your exploration will lead to the next groundbreaking application of polycubes, or inspire a whole new field of mathematical inquiry. The possibilities, much like the number of polycube arrangements, are truly endless.
That's a fantastic thought to end on. Thanks for joining us on this deep dive into the world of polycubes. Until next time, keep exploring, keep learning, and keep asking, what's the connection?